All right, our final video of the week. So again, hopefully you've staggered these out properly because nothing you have in these videos is required for either the quiz on Friday or for any of the homework or labs. So we'll look into this more next week as appropriate. So we're going to conclude our work here on mid-latitude cyclones. The idea that we are trying to look at the different parts of the puzzle, so to speak, to put together a mid-latitude cyclone. And then we're going to really move forward from mid-latitude cyclones and start to talk about how we forecast them and some of the impacts from various features associated with mid-latitude cyclones. So what we established in the previous video is the idea of the coupling between the surface and the upper levels. That different flow in the upper levels can support cyclogenesis, this divergent flow that occurs out ahead of a trough in the upper levels helps to instill rising motion throughout the troposphere and deepen a surface low pressure system. And so the term here is cyclogenesis. Genesis is birth of, and so we're talking about the birth of a cyclone. And the idea that this is all connected, we're going to look for that feature aloft to be the catalyst to cause a wave along a pre-existing boundary to start to deepen and strengthen and basically wrap up into a mature cyclone. And so what you're going to see is as the rising motion occurs and the pressures at the surface start to decrease, as we start to lower that pressure at the center of a cyclone, you're going to increase your pressure gradient. And we know that the stronger the pressure gradient, the stronger the pressure gradient force. And so this ultimately means that as you get a mid-latitude cyclone developing, you're going to start to increase the winds, and those winds are going to rotate inward. And so this is going to be your pleasant or non-pleasant, depending on your perspective, reference back to surface wind balance when we're looking at pressure gradient force, Coriolis force, and friction all coming together to produce a resultant wind. And so in the northern hemisphere, we're going to see that counterclockwise rotation, and that's going to be both counterclockwise and inward at the surface due to the frictional force. And that inward motion to the wind vector is going to cause that convergence near the center of a mid-latitude cyclone and continue to enhance that upper motion. And so here you see another interesting schematic, AB across the top, CD across the bottom, even though it looks like you might go top, bottom, left, right. So you can see the A, B, C, and D here in the corners. And so what you have here is some dashed lines signifying what's going on in the upper levels, and then the low with the boundaries showing what's going on near the surface. So again, early on, we got a wave that's developing. You're well ahead of your upper level trough axis here, and so that divergence is going to help this to strengthen. You can see this trough is relatively deep here in B. We're at a mature stage of our mid-latitude cyclone, but the trough axis is now much closer to your low. As we start to occlude, we now have basically a low at the surface and a low aloft. We don't have that tilt back to the west with height that was important to get the strengthening. And that's going to continue to become enhanced as our system weakens over time. Remembering again that once you see this occlusion occur, it means that the parent cyclone is starting to weaken. And so this is related to what we refer to as the conveyor belt method. And we're going to have a couple of slides coming up here shortly to give a little bit of information on different conveyor belts, a warm and a cold conveyor belt in particular. And so what you've seen with this spin, this counterclockwise motion around a mid-latitude cyclone in the northern hemisphere, is what we oftentimes see on satellite. And you can almost picture, if you look, for instance, in this upper left image, where you might have a low pressure center somewhere here across Nebraska, maybe an occluded boundary out towards eastern Nebraska, some type of warm frontal boundary draped across the Midwest. And then you can even see where the trailing cold frontal boundary through Kansas, Oklahoma, Texas. Here, low pressure somewhere maybe near St. Louis or west of St. Louis, some type of warm frontal boundary trailing out through the mid-Atlantic with this expanse of clouds. Again, what we're trying to do is think here about what we had in our earlier schematics with boundaries and where we would expect clouds and precipitation. Much thinner bands usually associated with the cold front, more sharp lift with that cold air wedging in. And so here we can illustrate this idea of conveyor belts. This is a little complicated, to be fair, and we keep it generally on the more simple side, but the idea here is we're looking at this from a three-dimensional perspective. It is convenient and in many ways easier to look at our mid-latitude cyclones as two-dimensional, but we know very well by this point in this lecture series that they are anything but a two-dimensional feature, that they are interlinked between what's going on the surface and what's going on aloft. And so in this example, we can see three different conveyor belts, a warm, a cold, and a dry conveyor belt. So we can start with the warm conveyor belt. The idea that this is originating near the surface and that warm, less dense air is forced to rise up and over the cold dome. So think of the behavior that we saw associated with our warm fronts. And this is going to help to catalyze a lot of widespread precipitation along and ahead of your warm frontal boundary, because this air that's originating down here is typically maritime tropical in nature, and so it has considerable moisture to work with as it's lifted upward. And we haven't spent a lot of time talking about it yet, but this lifting mechanism is what oftentimes is going to be the trigger to create clouds and precipitation. Your cold conveyor belt effectively is cold air, more of maritime polar, but it could be a continental polar air mass that's slowly gliding upward and then wraps around the backside of your low. And so this is bringing more cold air, that may interact with some of this warm air. And in many ways, this more moist characteristic of your cold air that's originating out ahead of your warm front relative to what's behind your cold front means that this can sometimes help to trigger some widespread snowfalls. One thing we'll see is that this area north of the cyclone track is often the area preferred to see long-term periods of snowfall and therefore some of our heaviest snowfall amounts. Finally, we may see what's known as a dry conveyor belt, originating high up in the atmosphere and sinking downward. And again, what we'll see over time is rising motion associated with clouds and precipitation, sinking motion associated with calm conditions, or shall I at least say clear and dry conditions. And so this is why we often see behind a cold frontal boundary a pretty, quiescent pattern, maybe a little breezy at times, and oftentimes cold, but not to where we have a lot of precipitation falling far behind our cold frontal boundary. And so we can look at the exact same arrows, again, just to prove that to you, three arrows in general, and looking at, again, all the boxes here are the same as on the previous slide as well, but now we're basically putting this into the context of a satellite image associated with the mid-latitude cyclone. Bringing that warm, moist air, large expanse of clouds and precip out ahead of our warm frontal boundary, cold air wrapping around, and a lot of this area up in here may be where there's snowfall or some heavier precipitation occurring, and then this dry air wrapping in behind and kind of that little slot in our comma here associated with that sinking dry air mass. So we transition a little bit here to talk about how do these cyclones move, or shall we say the preferred tracks for our mid-latitude cyclones. And so you can see here we'll have a couple schematics, couple slides worth, indicating the genesis locations, or at least some of the areas that are more preferred to see lows strengthen over time, and where they might move. The one thing you can note here is that overall we expect our lows to move from west to east. Again, the idea that we're in this area of circulation known as the westerlies. And so we can see the low pressures again forming over areas that are either A, proximity to between water and land, so we get a gradient of water and land, maybe some temperature as well as moisture gradients that occur in these regions. So off the northwest coast, down here in the Gulf of Mexico, again, a lot of energy within this warm waters of the Gulf, and similarly with the Gulf Stream, some pretty warm waters to generate East Coast lows. So we see the term Hatteras low here. The other area that sees a lot of preferential treatment, so to speak, for low pressures to develop is going to be in the lee of terrain. So we can see Colorado low on the east side of the Rockies, Alberta clippers that start to form on the east side of the Canadian Rockies. And we're going to see again, I think I alluded to this in an earlier video, we may expect a low pressure this weekend to develop somewhere here in the lee of some of the New Mexico terrain, and just really slowly lift, and potentially some areas in here getting dumped on with snow over the course of the weekend. But you can see, depending on the track of these Colorado lows, we can see some pretty close proximity to Valpo and Chicago, where we may see some heavy snowfall depending on where we are relative to the track. And so if we think of the most prolific snowfall producer, it's typically going to be one of these Colorado lows, especially if they can form a little further south here and come up through, say, St. Louis and Indianapolis, where we're on the north side and some of the colder air to be able to get some of those heavier snowfalls. And so this also depicts some of the motions of your cyclones. Again, Alberta clippers are originating from high latitudes, and so they don't necessarily have the chance to tap into a lot of the moisture that we find down here in the Gulf. So Alberta clippers can produce some snowfall, and we actually saw a lot of Alberta clipper type systems occurring over this past winter, dumping a little bit of snow, but nothing too bad. When we see these Colorado low tracks, or even some of these panhandle hooks that come up towards our area, depending on where we are, we can get some of the heavy snowfalls within these scenarios. And then we'll talk a little bit later on about some of these Texas lows and East Gulf lows, ones that come up the East Coast and can be prolific weather producers for a lot of the Northeast. We'll talk about the term nor'easter here shortly. And so again, looking at where do these originate? Lee of terrain, Alberta. Lee of terrain, North Rockies. Lee of terrain for the Colorado and Panhandle. Over water, North Pacific, South Pacific. East Gulf for Texas lows. West Gulf for Texas lows, and then is East Gulf lows as well. And we don't get into a lot of what the rationale is behind why we see areas in the lee of terrain. And by lee, we mean just downwind of where we see air flowing over the mountains. In general, the air flows over the terrain, and then it's going to have the tendency to sink a little bit towards the equator in this example. And that's going to help to spin up a trough and where we might see some lows develop. To be fair, you don't necessarily need to understand the reason for why it develops in the lee of terrain. Just understand that these are going to be areas more commonly, or more associated more commonly with the development of low pressure systems. And so this slide, I'm going to really quickly go over. The idea is we're going to look at this next week, assuming we're back in person. And this is good stuff that you will want to know before you get ready for exam number 2. What type of weather would be associated each of these areas, not only at the time of this image, but what's going to happen over the next 12 to 24 hours. And so I encourage you, even if you want to pause this video for a moment, to just think about the weather that would occur at all 6 of these letters in terms of temperature, how the pressure would change over time, rain and snow, and also the winds. Again, consider that we're in the westerlies, so we can envision that this is going to move somewhere here from what's at the Minnesota-Iowa border. Anticipate that it would generally move across central Wisconsin and into northern Michigan over time. And so we'll conclude our series here on mid-latitude cyclones talking about bomb cyclones, and in particular the superstorm of 1993. Bomb cyclones, or one term that got embedded really well into many of the media outlets, was bombogenesis. And to be fair, bombogenesis is a real term. A bomb cyclone is going to be one that deepens by at least 24 millibars within a 24-hour period. The at 60 degrees north is the technical definition, but in reality that's rarely looked at too deeply unless we're doing some type of deep scientific study. Regardless, at least 1 millibar per hour for a 24-hour period is what we look to find for a bomb cyclone. And so these usually occur in either the interface of land and water or over water. The necessity to have some type of really intense heating source. So for in this example, we see it forming here off the mid-Atlantic coast. We know this Gulf Stream out here has warm waters that work their way pretty far north in terms of latitude. And so that effectively is the fuel, the latent heat release, going back to another term from weeks ago, becomes a big deal with helping these systems to develop. So in reality, this probably was a mature cyclone somewhere over the central and even the eastern United States, became occluded, and you may have had reformation off the eastern seaboard. And so some of the strongest nor'easters, that's another term that we use for some of these really intense storms. Don't know what I bumped there. But the idea that these are going to be storms that develop and intensify, very strong wind producers, potentially heavy snow producers. And if we have time later in the semester, we're going to watch a video on the storm of the century. That was going to be your lab for this week, watching the video and having a response to the video. But with everything going on related to the virtual learning environment, I felt it was best to cancel that lab for the time being. But here is a little bit about the storm, the superstorm of 1993. Getting to be a lot of years ago, but still one that is brought up quite frequently when talking about some of the more intense nor'easters that have affected the United States within the last 50 to 100 years. Here again, we see a strong boundary between the cold land and the warm water. We had prolific numbers of tornadoes and thunderstorms over states like Florida. We had a cold front that was dropping temperatures rapidly in Cuba. Yet we also had a big influx of warm air working its way up the eastern seaboard and over a foot of snow across areas of central Alabama. And so this moisture source here, this area of warm waters of the Gulf, this area of the Atlantic with the Gulf Stream, effectively was going to increase the amount of latent heat being released. We had our temperature gradient, we had a latent heat release, and the general process with that is your water vapor condenses, releases that latent heat, and that's the fuel to increase your storm strength. We've talked a lot recently about pressures, and here we got a pressure mid-latitude cyclone of less than 980 millibars and a lot of isobars, tight packing of our isobars, that intense pressure gradient. And so you can envision what some of the winds would be in this scenario. If we look at the upper levels, you can see an incredibly deep trough, an axis extending here from Hudson Bay down through the Great Lakes, down through Memphis, Tennessee, and into the Gulf. And so we're out ahead of it here again. Some difluence helping to strengthen your mid-latitude cyclone. Again, where is this upper level trough? It is off to the west of where we saw in this previous slide where your surface cyclone would have been located. And so we look at the actual evolution of the storm within a relatively short amount of time. The fact that we had areas get feet and feet of snow is actually even more impressive when you consider the fact that this storm actually developed and moved quickly. This is over a 2-day period. It moved from near Galveston, Texas, all the way to the coast of Maine. And so you can see here, 7 a.m. on March 12th, 1,000 millibars. And less than 1 day later, we had dropped by 25 millibars. It was already a bomb cyclone by this point. Between 4 a.m. and 4 p.m. on the 13th, 12-hour period, it dropped another 15 millibars, so it remained a bomb throughout this entire stretch. And then as you can see here, we are bringing that warm front and cold front closer together. We're beginning to occlude, and as we see this system occlude, you can note that the pressures were already starting to rise. Regardless, we went from a relatively weak, compared to what it got to be, storm of 1,000 millibars, all the way down to an incredibly intense 960 millibar storm in basically a day and a half. So again, 25 millibar drop in 21 hours, another 15 millibars in 12 hours, but once it occludes, we started to have the system weaken. And so even with the fast motion of the storm, we saw considerable amount of snowfall over a large area of the country. If we have a chance to watch the video, it'll do a really nice job of depicting some of the societal impacts of this system. But even down here, it doesn't necessarily stick out because of these reds and dark blues, but you see this cyan type color, still 10 to 20 inches of snow. Areas 10 to 20 inches of snow down here in Alabama. These are areas that do not have snow removal equipment. And so this basically crippled areas such as Birmingham, Alabama, and Atlanta, Georgia for long periods of time. And then a lot of these areas higher terrain, 3 feet to 4 feet of snowfall. On the warm side, in the maritime tropical air mass, we saw a squall line with dozens of tornadoes occur. 44 deaths, unfortunately, occurred over this system as well. And with that pressure gradient associated with the storm combined with the squall line, we saw some areas with over 100-mile-an-hour winds as this ravaged the state of Florida. And so we conclude with this slide. I wanted to get it in under 20 minutes, and I'll be right there. Here we see it over the panhandle of Florida, the center of the cyclone, and we can see some of the clouds and other associated features with the superstorm all the way up into Canada. And so this is one of the hallmark signals of the superstorm of 1993. The fact that it was a massive storm stretching from areas well south of Cuba into Central America. We can even see the impacts all the way up into Canada. And so as this moved quickly up the eastern seaboard, you could have areas back here that would have been on the backside of your mid-latitude cyclone and simply had prolonged periods of time, cold air entrenched, and be able to produce that heavy, heavy snowfall. All right, we made it through our videos for 2 days of this week. Stay healthy and let me know if you have any questions, and hopefully we will see each other in person next Monday. Take care.